In this episode, we're going to get comfortable with a security control that people often talk about as if it is a protective shield you can simply switch on, but that actually works best when you understand its strengths and its blind spots. A web application firewall, WAF, sits between users and a web application and tries to filter or block malicious requests before they reach the application's code. That sounds straightforward, yet beginners quickly discover that web attacks do not always look like obvious bad traffic, and normal business traffic can sometimes look suspicious. If you treat a WAF as a magic barrier, you can end up with a false sense of safety, and that is a dangerous place to be in security architecture. The real skill is learning where a WAF provides meaningful risk reduction, where it only provides partial help, and where it can fail completely unless other controls are in place. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. A solid way to begin is by separating what a WAF is meant to protect from what it cannot realistically control. A WAF focuses on the application layer, meaning the content and structure of web requests and responses, rather than just the network path they travel on. That usually includes things like request parameters, cookies, headers, and the patterns that appear in requests when someone is trying to exploit a weakness. In simple terms, it is trying to spot and stop suspicious behavior that targets application logic, such as attempts to inject code, bypass access checks, or abuse input fields. What it is not, however, is a replacement for building secure applications, because the WAF only sees what passes through it, and it only interprets what it can parse and understand. If the application itself is flawed in its authorization logic, a WAF might not detect that a valid-looking request is being used in a malicious way. Understanding this boundary keeps you from expecting the WAF to do a job it was never designed to do. When a WAF helps, it often helps by making common, noisy attacks less effective and less disruptive, especially attacks that have recognizable patterns. Many attackers use automated scanning tools that spray common payloads across many sites, hoping to find one that responds in a vulnerable way. A well-tuned WAF can block these low-effort attempts, reducing the chance that a basic exploit works and reducing the background noise your application team has to investigate. It can also enforce certain safety constraints, like rejecting requests that are clearly malformed, too large, or otherwise inconsistent with normal behavior. In cloud security, this can be especially valuable because public-facing services are continuously probed and the scale of automated scanning is relentless. By filtering obvious abuse at the edge, a WAF can reduce load on the application and on downstream services. That load reduction can be a real availability benefit, not just a security benefit. Another place a WAF can provide strong value is when it is used as a compensating control while an application vulnerability is being fixed. In real environments, teams sometimes discover a weakness, but the code fix takes time because it must be tested, deployed, and validated. During that gap, attackers may already be attempting exploitation, and doing nothing while you wait for a code release can be risky. A WAF rule that blocks the specific exploit pattern can reduce immediate exposure, buying time for a proper fix. This is not because the WAF is better than fixing code, but because it can act faster in the short term. In a cloud environment where deployment pipelines may be complex and multiple services may depend on one another, that time buffer can be critical. However, it only works if you treat it as temporary risk reduction and still plan the real fix. If you leave emergency rules in place forever, you may end up with a fragile system that depends on complex filtering instead of clean application logic. WAF designs are also useful when you think about them as policy enforcement at a boundary, not only as attack signature blocking. Many modern WAF configurations can enforce behavior expectations like which methods are allowed, how quickly requests may arrive, and what kinds of content types the application should accept. That kind of rule can help prevent abuse that might not be a classic exploit but still causes harm, such as scraping, brute force login attempts, or request flooding that overwhelms backend resources. It can also help enforce consistency across multiple applications by applying a shared baseline, which is helpful when teams build services with different levels of maturity. In cloud security, where many teams deploy services quickly, a shared baseline can reduce the chance that a new service is exposed with dangerous defaults. Even so, baseline protections must be carefully balanced because overly strict rules can block legitimate traffic, and overly loose rules can create a boundary that exists mainly for show. At the same time, it is essential to understand where WAF protections can fail, because failure often happens in ways that are subtle and easy to miss. One major limitation is that a WAF mostly sees patterns, not intent, and many serious attacks use valid requests in harmful sequences. For example, if an application has broken authorization, an attacker might access another user's data by simply changing an identifier in a request, using the same normal request format a legitimate user would use. That kind of flaw is often called insecure direct object reference, IDOR, and it tends to slip past a WAF because the request does not look like an exploit payload. The same issue appears when business logic is abused, such as manipulating a shopping cart or abusing a refund workflow using perfectly normal requests. The WAF cannot easily know the business meaning of every request, because that meaning lives inside application logic and state. This is why architects treat WAF as one layer, not the layer. Encryption can also create blind spots if you do not design the traffic path carefully, because a WAF cannot inspect what it cannot see. When traffic is protected with transport layer security, TLS, the content of requests is encrypted between endpoints, and that is good for confidentiality. However, it also means that for a WAF to inspect application content, it typically needs to be placed where it can see decrypted traffic, which requires careful boundary design. If the WAF is positioned in a way that only sees encrypted traffic and cannot decrypt it, its ability to detect and block application layer threats is limited. If the WAF does perform decryption for inspection, that introduces a trust and key management responsibility because the WAF becomes part of the sensitive path. In cloud security, this is especially important because traffic might pass through load balancers, gateways, and service meshes, and it is easy to assume visibility exists when it does not. Architects must be explicit about where inspection occurs and what parts of the system are trusted to handle decrypted data. Another common failure mode involves modern application interfaces that do not look like traditional web forms, especially application programming interface, API, traffic. API calls often carry structured data formats and can involve complex authentication tokens, nested objects, and patterns that are specific to an application's design. A WAF can still provide value here, but generic signature rules often struggle because the traffic patterns are highly varied and the meaning is tightly tied to application context. Attackers can also exploit logic errors in API design, such as calling endpoints in unexpected orders, requesting data that should not be exposed, or abusing rate limits in ways that look normal at the request level. If you assume that a WAF automatically secures APIs, you can miss important needs like strong authorization checks, schema validation, and careful error handling. In cloud environments where services talk to services constantly, API security becomes a core architecture concern, not an edge-only concern. A WAF can reduce some risks, but it cannot replace application-aware controls that live inside the service. Even when a WAF has good rules, it can fail because of how attackers adapt, especially when they test and tweak payloads to evade detection. Many WAF rules rely on known patterns of malicious input, like certain characters or certain sequences that often appear in injection attacks. Attackers can sometimes bypass these patterns by encoding payloads differently, spreading payloads across multiple fields, or using uncommon syntax that still triggers vulnerabilities. A WAF can be improved to handle these evasions, but that tuning takes expertise and ongoing attention, and it can never guarantee perfect detection for every possible variation. This is not a criticism of WAF technology so much as a reminder that pattern-based defenses have limits in a creative adversarial environment. In cloud security, Where applications are public and accessible, attackers can test freely and iterate quickly. That means WAF protections must be combined with secure coding, strong identity checks, and monitoring, because no single layer will catch everything. The best architectures assume bypass attempts will happen and plan containment accordingly. Availability and performance also matter because a WAF sits on a critical traffic path, and any problem in that path can affect the business immediately. If a WAF is misconfigured or overloaded, it can block legitimate customers, slow down responses, or cause timeouts that users experience as an outage. This is why you cannot design WAF controls without thinking about resilience, capacity, and safe change management. In many cases, security teams want very strict blocking rules, but operations teams want very low false positives, and the best solution is to use a learning and tuning process rather than forcing strict rules instantly. Architects also plan for fail-open versus fail-closed behaviors, meaning whether the WAF should allow traffic through if it cannot make decisions or whether it should block everything, and each choice has consequences. Fail-open can preserve availability but may allow attacks during a control failure, while fail-closed can preserve security but create outages. Choosing that behavior should be a deliberate policy decision based on risk, not an accident of defaults. It also helps to remember that a WAF is only one part of a broader boundary design, and it can be undermined if other paths reach the application without passing through it. This is one of the most common ways a WAF fails in practice, because environments often have multiple entry points, such as internal service calls, partner integrations, administrative interfaces, and testing endpoints. If an attacker can reach the application through a path that bypasses the WAF, then the WAF provides less protection than people assume. In cloud environments, bypass can happen through misconfigured security groups, direct access to service endpoints, or alternative load balancer paths. Architects prevent this by ensuring that the WAF-protected entry point is the only entry point for the traffic types it is meant to govern, and by locking down direct reachability to backend services. This is an architectural discipline problem as much as a technology problem. A WAF should be part of a clear, enforced boundary, not a decorative layer applied to only one of several doors. Good WAF use also requires thinking about what you want to learn from it, because visibility is often as valuable as blocking. WAF logs can show scanning behavior, attack trends, and suspicious patterns that can guide patching priorities and incident response. However, logs only help if they are collected, protected, and reviewed in a way that supports action, and that means integrating WAF telemetry into broader monitoring. Beginners sometimes assume that if a WAF is blocking attacks, the problem is solved, but the blocked traffic can be a signal that someone is targeting a specific endpoint or that your application may have unpatched weaknesses. The WAF can also reveal false positives that indicate legitimate clients are being disrupted, which affects both business outcomes and trust in security controls. Architects therefore design logging and alerting thresholds so that important events are visible without overwhelming teams with noise. When logging is well designed, a WAF becomes part of an early warning system, not just a filter. To use a WAF effectively, architects also connect it to secure development practices, because the strongest outcome is when WAF protections and application improvements reinforce each other. If the WAF detects repeated injection attempts against a specific parameter, that can prompt a deeper review of how that input is handled in code. If the WAF reveals abuse of a login endpoint, that can prompt improvements in rate limiting, account protection, and user experience. Over time, this feedback loop can reduce dependency on complex WAF rules because the application becomes inherently safer. That is important because over-reliance on WAF rules can lead to brittle configurations that are hard to maintain, especially when new features change request patterns. In cloud environments where deployments happen frequently, brittle rules can become a constant source of production incidents if not managed carefully. The healthier approach is to treat the WAF as a layer that reduces risk while the application and identity systems do the deeper work of correctness. That combination supports both security and operational stability. Another aspect beginners often miss is that WAF decisions are policy choices, not only technical choices, and those policy choices should match the organization's risk tolerance and mission. Some systems can tolerate aggressive blocking because the user population is controlled and predictable, while other systems must be careful because they serve diverse clients with many legitimate request variations. Some systems handle sensitive data and require stricter protections, while others handle low-risk content and may prioritize availability above all else. In cloud security, policy choices also include how you handle bots, rate limiting, and geographic access patterns, because these affect both abuse prevention and customer experience. The key is to make policy explicit so teams understand why certain rules exist and how to change them safely. When policy is unclear, rules become a patchwork of reactions to incidents, and that is where fragility grows. A well-designed WAF strategy includes a clear purpose, a tuning process, and a plan for evolving controls as the application evolves. As we pull these ideas together, the main lesson is that a web application firewall, WAF, is most valuable when it is treated as a smart boundary layer that reduces exposure, blocks common attacks, and provides actionable visibility, while still recognizing that it cannot fix core application flaws. It helps when the threats are pattern-based, when you need compensating protection during remediation, and when you can enforce consistent baseline behaviors at the edge without harming legitimate users. It fails or becomes less effective when attacks use valid requests to exploit business logic, when encryption placement hides traffic from inspection, when API complexity exceeds generic pattern matching, or when alternate paths bypass the WAF entirely. It can also create risk if it becomes a single fragile choke point that harms availability through misconfiguration or overload. The most durable architectures use WAF controls alongside strong identity, sound authorization, secure coding, segmentation, and monitoring, so that no single layer is expected to be perfect. When you know where the WAF fits and where it does not, you can apply it confidently, avoid false confidence, and build boundaries that stay clear as the system grows and changes.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.